Hello everyone, welcome to Gyandeep, a channel where we talk everything about data science. This is the third video that we are recording for the Kaggle competition series that we started. Right, the first two videos, if you have not referred to them, right, I would suggest you to refer them first and then come back to this video. Okay, so let's do a quick recap of what we covered in session 1 and 2 or part 1 and 2 of this series. So we started by importing the libraries. We imported pandas, then we also imported transformers and essentially auto model and auto tokenizer from transformers. Then we did import the torch library, numpy, sklearn in order to perform the train test split and matplotlib, right? And then we loaded the data. So we had train, test, and sub. My data looked like this. We defined the config. We essentially had a model which is birth, base, uncased, and we also provided dropout to be 0, max length to be 512, and we would run it for 4 epochs, and we had a batch size of 16. Then we had the tokenizer. The tokenizer is essentially auto tokenizer and dot from pre-trained config model. So whichever model we defined, it would automatically take the tokenizer, pick the tokenizer for the same. Now, next we defined the feedback dataset class. We had the method called get item, where for each of the items we essentially got the sample and then we tokenized it and we created the inputs here. So it had the three keys: input IDs, token type IDs, and the attention mask. Next, if it is an is test, that means if we are in the test phase, then it just returns inputs, while if it is in the training phase, it also returns the targets or the levels, right? So we'll run this. Then we had the train data being split. So we did the train test split. We got the train DF and the validation DF. And then we had the feedback dataset class. We then loaded it in the torch through the torch.utils.data.data loader, right? And then we defined the model architecture where we had the where we had the two fully connected layers. So essentially, the first one being 64 layers and the second one being equal to num classes, which was 6 in this case. Right, so this is my feedback model. Now, the next thing that we did in the session 2 was we discussed about the trainer, the importance of it, and we also covered some of the key concepts like loss function and the we also talked about learning rate, optimizers, scheduler options, and so on, right? Now, in this session, as we discussed, we'll be going through the individual lines or the code, right? So let's try to understand what this class trainer does. So we first def init and we assign the values. So we have self-taught model is equal to model. We'll get this value in the next cell. Then we have the train loader and the validation loader, which is the loaders that we define. We have the config. This is already defined to be config. We create input keys, and this is a list. And this essentially is the key of the input that we created. We'll see why this is needed in the next few lines. Next, we had the loss function, and in this case, we take nn dot smooth L1 loss, and it is supposed to inherit the properties of both L1 as well as the L2 loss, and is supposed to be very much agnostic to the outliers, and that's why we are using here a smooth L1 loss. And then we gave the value for, assigned the value for the learning rate. We had the optim here. As we discussed, the more popular of the optimizers are Adam W. We are we are experimenting here. So we'll start with the Adam W. We define the model dot parameters, which will get updated, right? Depend, and also the self dot LR. These are the two arguments that the Adam W would be accepting. Now we had the scheduler options. In this case, it could be defined for three of these schedulers. So we had cosine, annealing, warm, restarts, and the way to define it is it's essentially in the LR underscore scheduler. So we do torch dot optim dot LR scheduler cosine annealing warm restarts, and then it takes on a few of the arguments as well, like we have to so the optimizer, we have to pass on the optimizer here first. So self dot optim t underscore 0, this is essentially the number of the steps before the restarts happens. So it will essentially warm up for 5 steps before the restart happens. And et underscore meaning means that its learning rate is 1e minus 7. Likewise, we define for reduce LR on plateau self.optim min, and this is the minimum LR that we have defined to be 1e minus 7. In case of step LR, we have the step size of the 2, that means reduce LR after every 2 epochs. So we have now the scheduler. So a self.scheduler, we provide the options, and in this case, my config scheduler is essentially cosine annealing warm restarts. Okay, now we have the placeholders. These are the train for the train losses, validation losses, and val MCR MSC. So these are the empty lists that we have defined for them, and they will contain eventually the values for each of these. Okay, so now let's get into the other methods here. The first one being the MCRMSC. We learned about it in the previous session. This is the mean column root mean squared error. And it accepts outputs and the targets as the argument. It first calculates the root mean squared error. So we get the call wise MSC here. Torch dot mean, torch dot square, targets minus outputs, and dim is equal to 0, which means that there will be a row wise operation, right? And then that's why we have dimension is equal to 0. Next, we calculate it for the individual, we calculate it for the column. So we do the torch dot main, and then we do a square root of the column wise FSC that we got, and all the operation being performed row wise. That's how we get the loss. So my MCR MSC, this method is now available under the trainer class. Now, the next step is actually to define the workout, essentially the one epoch. And then we can iterate it over the multiple epochs that we want the model to be trained for. Like in this case, we have defined it for it to be 4 epochs, right? So we start by defining train underscore one epoch, self, comma, epoch, number of epochs. We start by having a running loss of 0, right? So this is all set to be 0 at the start. We also define the progress. We want to see how it's progressing for the length of the train loader. So we have TQTM self dot train loader, which is the data here, and the progress has to go on till the length of the train loader here. That's why length self dot train loader. Now we do the enumerate, so we'll get a tuple I comma and then inputs and targets. They are getting returned because we have, if you remember, is test is equal to false, right? So for I inputs comma targets in enumerate progress. Now the first thing that we do in the training phase is we put it on to the optim on a 0 grad. So there is no gradient at this point, 0 gradient at this point, and that's why optim dot 0 grad. Next, we have the inputs. Let's pass them to the through the device or CUDA in this case, and that's why k inputs k. So for each of the elements under under the for each of these case, we essentially pass the input to the to the device. Similarly, in case of the targets labels, we pass them to the device. Next, the outputs. So we generate the output through self-taught model inputs. Model is yet to be defined. That comes into the next cell. So, and now that we have the outputs, we get the loss. So, and this is loss underscore fn and outputs comma targets, which will essentially give us the loss between the outputs and the targets, or the outputs that we got and the targets which we have from the original data. We have then the running loss getting updated. So for each item, we update the running loss, and so it becomes plus is equal to loss dot item. So it every time it gets added. Now we have calculated the loss, so we backward propagated. So that's why we have the loss dot backward. At this point, if you remember, we have the gradients getting calculated. So for each of the parameter, we'll have the d by dx of the parameter x, right? So then the backward propagation has happened. Now the optim dot step will update those parameters. So we saw it earlier. So my parameters will get updated here. Next, we have the config scheduler. So in case my changes in the gradients are as per the are too low or too high, according to the scheduler that we have defined, the learning rate would change or would remain the same, right? So in this case, it says that if the config scheduler is cosine annealing warm restarts, then scheduler dot steps, that means you change it by epoch minus 1 plus I by length of the trailing loader. This is what the PyTorch doc says. That's how you change it or update it, right? So we have it here. Now, in case the scheduler is step LR, then again, depending upon the steps that you have defined, you get these the changes in the LR through this step. Now we calculate from in this training phase, we calculate the training loss by doing the summation of the running loss that happened, and we divide it by the length of the train loader. So as we can see here, the for loop ran till here and it got us the entire loss across all the row items, and then we divided it by the length of the train loader, right? And that's how we get the mean training loss from here. Now, in case of the validation, let's define the method. So we have again the running loss as 0, and in this case, I want to track my metrics, which is MCRMSC. So we have defined the MCRMSC as 0 again. We track the progress through the TQDM inputs. We get the inputs and the targets from the progress from here, right? And we get again we pass again the inputs and targets to the device. We get the output from the model inputs. Then we do the loss. We calculate the loss, right? Through this loss function, outputs comma targets. We add it to the running loss by doing the loss plus dot item. Then we have the running MCRMSC, which we update, right? For each of the item, my MCRMSC gets updated here. We calculate the two values here, and first one being the validation loss, which gets appended to my validation losses, right? So the list that I created earlier as a placeholder, and similarly my validation underscore MCRMSC, this gets updated with the running MCRMSC, the mean of the running MCRMSC. Okay, so that's about how we essentially define the train and the validation steps for a single epoch. Now let's define the steps involved in the fit, and that's pretty much simple. And so essentially, we track the progress, okay, and so it could be for multiple epochs that we want to track, right? So we define a TQDM here and provide it a range of 1 comma, and since we have given it a 1, so we add 1 here additionally here, right? And that's how we define the TQDM. Now for epoch in the fit progress, we which is now there are 4 epochs, right? So it will run for 4 times. So self dot model dot train, we have set the model in the training mode in this line, right? Then we do a fit progress, and essentially we are giving a description here which would say that for this epoch, which is the first epoch here, right? And so the self.config epochs, right? One, right, out of 4, and the training, so it just gives me some description of what is happening. It trained for 1 epoch, right? And this is the first one that is getting trained. We pass the value of the epoch as we saw earlier. Then similarly, we do it for the evaluation side. We set the model on the eval mode. We do the fit progress, and we have the set description for each of the epochs, and the valid 1 epoch is run for the epoch here. Next, we print the values of the train and the validation loss here. So we can see it readily on the console. Anything and that we are accumulating, just to be very sure we that we are optimized on the memory, we sort of collect the garbage, and we also empty any cache that might be there in torch.cuda. Now we have the trainer steps has been now completed. So just to give a quick recap, we started by assigning the values here. Then we did the MC. We defined the matrix, which is MCR. Then we defined the steps for 1 epoch, train 1 epoch. We defined the steps for validation 1 epoch. I think I forgot to mention here about torch, this decorator torch.nograd, which means that there will be no gradient calculation during this method, which is valid underscore 1 epoch, because there is no loss backward here. I do not want to calculate the gradients. That's a wastage of my compute memory, and hence I define torch.nograd. Okay, then we essentially did a fit. We defined the fit, right, and method, and okay, so those were the steps, and we also cleared it for any garbage that might have been collected, right? Now let's define the model. Model is equal to feedback model config to device config device. So we have now the model being shared with the device. We have the trainer underscore final. Now this one is essentially the trainer model, and trainer loader, val loader config, and we have given an initial learning rate of 2e minus 5. Okay, so this is the step where we have defined the trainer final, and which is of the trainer class. Now let's do the fit. So here we call the trainer underscore final dot fit. At this point, I will take a pause, and we'll let this finish. And once this model training is done, we'll talk through the evaluation parameters and so on. Okay, so the trainer underscore final dot fit has eventually trained it for the 4 of the epochs. So we can see the train and the validation loss here. So epoch 1, epoch 2, epoch 3, and epoch 4. Okay, So now we essentially delete everything that is unnecessary at this point. So post that we do the we get the losses and essentially convert them into the data frame. So we are so what essentially we are getting here is the epoch, the train loss that we gathered, the validation loss, and the validation MCRMSE. So let's see how the data frame looks like. So we have epoch, train underscore loss, validation loss, and val MCRMSE, and these are the respective values. Next, we generate a plot of it to see how well is the fit. So we see the train and the validation, and it's pretty much close, right? So that's it for this session, guys. I hope you liked it. And in the next session, we are going to cover the inference part of it. Thank you.